Awesome. So today is our first quantum algorithm. And what we're really interested in is showing that there's some motivation, some capability for quantum computers to be able to solve problems faster than classical ones can. We'll need to motivate a couple heuristics to solve this, but what we're going to be working on today to show this is going to be like a little simple problem, computational problem that doesn't really have like any useful value for us as programmers. But it's really nice for both building up some basic machinery that we're going to use in more advanced stuff like Shor's algorithm, Grover's algorithm, and also just for giving like a nice formal proof or formal intuition for why a quantum computer might offer a promise for an exponential speedup. So I'll dive right in, and the first thing we're really going to want to focus on is developing up some mathematical machinery. So let's talk about the Hadamard gate, because that's going to be like at the key of a lot of our quantum algorithms going forward. And it's going to be key behind this special speedup that we're going to try and leverage today. So our action of the Hadamard gate was to map 0 to our plus state, where that's just 0 plus 1 renormalized, and 1 to the minus state. And generally speaking, a Hadamard transformation is going to be basically just doing this, but with multiple qubits. So we're going to be taking like n qubits, let's say, in the input, and we're going to be applying a single qubit Hadamard gate to each one at a time. And notice that if we write out this output as some quantum superposition, there's going to be a lot of terms in it. I mean, if we've got n qubits, then there's 2 to the n possible basis states, bit strings we can form from them. And that's going to be a lot of terms to keep track of if we're just writing out our expansion in a way similar to what I've done here. So it'll be nice to find some sort of closed form summand for representing these coefficients, representing these relationships. And that motivates the mathematical question. Can we condense this at all? Can we come up with a simple expression for representing a Hadamard transformation on multiple qubits at once? So to do this, let's see if we can make some simplifications on our definition here of the Hadamard gate. The first thing I'd like to do is notice that the relative phase, and that really just means like the term between the 0 and the 1, whether it's a plus 1 or a minus 1. Notice that that's controlled by what the input is. Specifically, what I'd like to point out is that if our input qubit is 0, then when we apply a Hadamard gate, there is a plus 1 between the 0 and the 1, but more specifically, we can write plus 1 as minus 1 to the power of 0, like this. So, and similarly, when we work with the 1 qubit, and we apply a Hadamard gate to it, we get a minus sign, which can be represented as minus 1 to the power of 1. So notice that the exponent of minus 1 in both cases is equal to the value of the input qubit. So 0, 0, 1, 1. So this really suggests something nice, which is that we can turn this into a closed form, a general formula, so to speak, for the 1 qubit Hadamard gate, which instead of going case-wise and showing what the definition is for 0, what the definition is for 1, just for some arbitrary qubit x. And that's this form right here, just using that little intuition that we've developed right there. So this is great, but we're still writing out every term in the expansion. Granted, there's just 2 terms. There's a 0 term and a 1 term. But this is going to exponentially increase as we add more qubits. So we're going to need to introduce a new parameter, y. So the basic idea that I'm going to try to do here in building up a summand is recognize that a superposition is a sum of a lot of terms, right? And each of these terms is going to have a coefficient. So I'm going to represent the specific term, which is going to be some bit string, let's say 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, etc., as some variable y, and I'm going to represent the coefficient as a function of y. Let's make this a little more concrete. So if we go back to our Hadamard definition of x, the first thing we're wanting to do is to see if we can add some more negative signs, or more specifically powers of -1. Why do we want to do this? Well, if we're going to want some nice closed form summand, we're going to need to make it super compact, and the presence of a -1 acting upon the 1 term suggests that there's going to be a -1 involved in that special function of y. So notice that in both cases, the coefficient of 0 is just plus 1. But we can write that as minus 1 to the 0. And taking this a step further, since 0 times anything is just 0, we can actually write that exponent as 0 times x. It might seem a little silly what I'm doing here, making out all these expansions, but the nice thing is that we're getting a lot of really helpful generality. So in both cases, the exponent of the minus 1 amplitude is the input value x times y, or y is the value of the term that we're working with. So if we're working with the 0, then the exponent of minus 1 is 0 times x. And if we're working with the 1, the exponent is 1 times x. And this allows us to compactify this into a single term, a single nice sum end right here. We take the 1 over square root of 2, we move that to the front. We've got an input value x, and that's just going to be the sum over all possible basis states y with an amplitude of minus 1 to the x times y. And for our sanity check, let's just confirm that this works and does exactly what we expect for a Hadamard gate. Case-wise, if y equals 0, then, y equals 0 implies that h of x, or more specifically, that implies that xy is equal to 0. So we're going to get a plus sign, which is great. We got a plus sign in front of the 0 term in both the plus state and the minus state. Now, if y is equal to 0 and y is equal to 1 and x is equal to 0, then we're still going to get xy is equal to 0. And this is corresponding to the case where our input qubit is 1, but we're looking at the 0 term. So last but not least, if they're both 1, then that's the only case in which this negative sign becomes minus 1, because the exponent, that's the only case in which the exponent can be 1. So, okay, this clearly is doing what we want. So now let's go back and see if we can generalize this to multiple qubits. It might seem intimidating. This formula might seem like not particularly motivated, not particularly well constructed, but we're actually really, really close. And to do this, we're just going to use our tensor product that we've developed a couple lectures back. So more specifically, if we're applying a Hadamard transform on 2 qubits, let's say, that corresponds to applying the gate Hadamard, tensor Hadamard, on the input register qubit x1, tensor qubit x2. And we can, of course, move those tensor products over to say that this is going to be the Hadamard on x1 tensored to the Hadamard on x2. So now what we're going to want to do is we're just going to want to invoke our formula. And notice that we're going to have to sum over separate indexes. Index y1 and index y2. Now, don't panic. We're just going to do a little bit of algebra into condensing this sum. And specifically, we're going to want to see how we can collect the minus 1 coefficients. So doing that allows us to move this 1 over square root 2 and this 1 over square root 2 to the front. That's super easy and nice. Moving this term inside there, what we get is the minus 1 terms collect. They add minus 1 to the power of x1, y1 plus x2, y2. And of course, y1 and y2, since this is how our tensor product's defined, they kind of recollect and form a y1 and y2 term here. They're just describing our output basis vector in our superposition here. So this is just our product of our formula, first formula with itself. We're just working over 2 different binary indices, one for y1, one for y2. Now, we can turn this double sum back into a nice simple sum by introducing a new variable y. And this is just going to be the collection of the bits y1 and y2. It's just going to be a new bit string. Instead of a single bit, it's going to be 0, 0, 0, 1, 1, 0, 1, 1. And we're also going to introduce one bit of mathematical machinery, the bitwise product. Specifically, I'd like to address this term here, which looks a little scary. What we'd like to do is we'd like to be able to condense this to be just a term that's dependent upon our new variable y. And the way we're going to do that is we're going to define the bitwise product. X dot y is going to equal x1, y1 plus x2, y2 dot 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 x to the n, y, n. So in this case, like for a two-dimensional bitwise product, we can practice and show that like the bitwise product of, oh, shoot. It's fine. It's an 0, 0, dot 0, 1 is equal to 0 times 0 plus 0 times 1 is equal to 0. I paused the recording.
This is always so jank, man.
Did it help? Just like stopped.
Yeah.
I'm not quite sure. It's like, see, it's like flashing. Yeah, this is off, right?
Recording actually. We can edit it out later. It's fine.
It is what it is. Apologies. Sorry.
We can stop the recording for now.
Okay, so what we've done here is we've basically condensed this into a formula that's just dependent upon one nice variable, y, by introducing this bitwise product to deal with the exponent. Okay, great. Now, this just yields the following closed form for the two-dimensional Hadamard transform. 1/2 times the sum, and then notice that this is basically what we had before for the 1 cubic case, except now the only difference besides the power, the scalar in front, which is just a normalization factor, is that instead of a standard product, we've got a bitwise product in the exponent of -1. Great. And notice nothing about this specifically, or more, nothing about our logic in deriving this multiple cubic case was limited to n equals 2. Granted, we would have had multiple summands that we would have to condense, but the idea is exactly the same. Condense all the individual bits that you're summing over into one nice variable y, and rewrite x instead of being in terms of its bits just as x itself, and you get this nice, easy bitwise product in our exponent, and you get a nice general expression for the Hadamard formula for multiple qubits. So we're going to need this mathematical machinery multiple times over the next couple algorithms that we study. You don't have to understand it too well. I just wanted to derive it so that it just made it clear. But the main thing we want to just notice is that information is being stored and represented in the power of -1. And that's the main idea that we're going to try and manipulate later. It'll all come clear in time. So the next thing I'd like to quickly review is just a little computational tool called an oracle. And many problems in computer science involve this. If you've ever heard of a black box, it's basically the same thing. The idea of an oracle is that you've got some sort of computational resource which can basically check answers to a problem for you. With 100% accuracy, it doesn't really matter how it's built. We can honestly, that's why we say magic. It's kind of given to you. But the idea is you can feed potential input into this thing, and it can tell you it is a solution, it is not a solution. It can't tell you what the solution is, but it can check a solution you might already have on hand. So that's called a query. And queries are categorized as a computational resource, which is really useful if we're trying to compare classical algorithms to quantum algorithms, because that's a very simple thing to check, is how many queries did this algorithm require? So yeah, solutions get fed in and Booleans get read out. That's the basic idea behind oracles. Again, don't worry about how the oracle shows up. It's assumed to be given to you. In many cases in computer science, you'll have a problem where it's really easy to check a solution, meaning to program an oracle, but the actual thing that you're interested in is finding a solution. So this isn't really like some computationally infeasible presumption to be making. So yeah, and we're basically going to see what happens when we call an oracle on a superposition state. That's kind of the idea that we're going to try and build moving forward. Okay, let's develop our problem statement. So again, what I'm about to say is completely useless from a practical standpoint. This problem is just a toy, so don't take it too seriously. Rather, just try to step back and enjoy and kind of just develop some intuition for what's going on and why there's a unique quantum edge here. Just try and follow that. Try and visualize that this is just a proof of principle concept. So essentially, the Deutsch-Jozsa problem is given some oracle or some function, we'll just say. We'll be even more general. And this function takes in some bit string from 0, 1 to the n, so n bits, and it's going to output a bit, either 0 or 1. Furthermore, we have the restriction that this function is either constant or balanced. Constant meaning that no matter what bit string we input, we're going to get the exact same value from our function. So either it always returns 0 or it always returns 1. And balanced means that it outputs 0 for exactly half of the inputs in our space, and it outputs 1 for the other half in our space. Doesn't matter how this is partitioned. The point is that this is a promise problem. We're guaranteed to have a function that's either constant or balanced. So, and what we're going to do when our algorithm has made some decision about the nature of the function is it's going to print out 0 if the function's constant, or if it thinks it's constant anyway, and it's going to print out 1 if it thinks it's balanced. So, once again, the main two reasons we're studying this is going to show an example about how a quantum computer can be superior to a classical approach. And it's going to give a concrete idea for how to approach problems quantumly. Because actually, some of the famous algorithms you might have heard of, Simon's algorithm, Shor's algorithm, are actually basically the same thing as this, just with a little more fine-tuned mathematical machinery. But the actual concept's basically the same. This will come clear in time, but yes, that should be enough to motivate you guys here, that we're building some machinery that's going to be used in some really flashy algorithms later. So, yes. So let's think about the worst case behavior of a classical algorithm, a classical approach to solve this problem. Well, what would you do? You just check answers. You'd feed in possible bit states, and the function would say yes or no. It would say 0 or 1, and you'd basically look, okay, how many times has it output 0? How many times has it output 1? Well, if you get 0 sometimes and 1 some of the other times, then it's guaranteed to be balanced because that's the only category that fits that sort of output. In the worst case, you draw the same value of the function 2 to the power of n minus 1 times in a row. Again, is this probable? No. But we're just interested in the theoretical worst case behavior of this classical algorithm. And then we need to call the function one more time in order to have measured over half the search space to completely rule out that the function cannot be balanced, that it is 100% constant. So this makes it an exponentially hard problem in the worst case, at least for deterministic approaches, which are all that we're going to study here because it's kind of outside of this discussion to consider probabilistic algorithms. But yeah, and I'll give some examples. Here are some functions, and 2 of them are constant, 2 of them are balanced, and it's pretty easy to spot which is which. If we're just taking in some bit string, which can be, a bit, 0 or 1, a one-dimensional bit string, then these 2 functions are clearly constant. This one always outputs 0. This one always outputs 1. And on the right, the function that just outputs whatever it's been given, well, that's clearly balanced because half the time it's given 0, half the time it's given 1. And the function that gives the opposite of what it's been given is also a balanced function. That just balanced in the other direction with the other partition. So essentially what our computer is going to want to do is it's going to be given some function. It's going to be allowed to test it as many times as it wants, but preferably as few times as possible. And it's going to put it into one of these 2 columns. So now I'd like to turn the mic over back to Ian, and he's going to start developing some of the basic quantum intuition that we're going to use to address this problem from a quantum perspective.
All right, yeah, thank you so much, Gus. So I will discuss the quantum solution to the Deutsch-Jozsa algorithm, and the first thing we have to do is we want to talk about a important concept called phase kickback. And to do that, the first thing you have to do is I want to sort of prove this equation over here, the 1 over square root 2 times y XOR 0, right? Or that's also mod to addition, minus y XOR 1. By the way, y in this case is just going to be an arbitrary bit, either 0 or 1. And I want to show that it's equal to negative 1 to the y power times the minus state, right? 1 over square root 2 times 0 minus 1, that's the minus state. And yeah, if you look to the right, this is just like another way to write that. Y XOR minus is equal to negative 1 to the y times minus state, right? So one thing I want to like mention though is that I'm going to represent the 1 over square root 2 y XOR 0 minus y XOR 1 as y XOR minus, right? Technically, this is abusive notation. This expression is actually like illegal. You can't actually write it down this way. But the idea that I want to represent is that like this expression is like the minus state, right? But I'm just replacing the 0 with the product of y XOR 0, and I'm placing the 1, right, with y XOR 1, right? Like, if you substitute in the 0 for y XOR 0 and substitute the 1 for y XOR 1, it looks identical to the thing I want to prove. Anyways, this expression is true for y, right? Y is an arbitrary bit, 0 or 1. That's only two possible cases. So all we need to do to prove that this is true, we just have to walk through the two cases where y equals 0 and where y equals 1, right? In the case of y equals 0, we start with our starting expression. 1 over square root 2, y XOR 0 minus y XOR 1. And, we just plug in 0 for y, right? Because this is a case where y equals 0. So we get 1 over square root 2, 0 XOR 0 minus 0 XOR 1. 0 XOR 0 is going to be equal to 0 because 0 and 0 are the same number. And 0 XOR 1 is going to be equal to 1 because 0 and 1 are different numbers, right? So what we right now have here is 1 over square root 2 times 0 minus 1, right? If you notice here is that we can just pull out a 1 because, that's just an identity. You can always pull out a 1 whenever you want to. And we're just going to turn the 1 into negative 1 to the power of 0, because anything to the power of 0 is going to be equal to 1. And it seems kind of arbitrary for now, but it'll make sense why I'm doing this in a sec, right? Anyways, we have the form negative 1 to the 0th power times the minus state, right? And if you recall, this is a case where y equals 0, so we actually get negative 1 to the y power, right? Because y equals 0 times the minus state. And we'll basically conduct the same process for the case that y equals 1, right? Once again, we start off with 1/2 times 1 over square root 2 times y XOR 0 minus y XOR 1, right? Once again, we plug in 1 for y, and we get 1/2 1 over square root 2 times 1 XOR 0 minus 1 XOR 1. Conduct the XOR operation inside. 1 XOR 0 is equal to 1. 1 XOR 1 equals to 0. And we have this expression here, 1 over square root 2, 1 minus 0, right? First thing I'm going to do, I'm just going to rearrange these terms, like the order, right? Then I notice that we can actually pull out a negative 1 from this expression to bring back 0 minus 1, right? Pull that negative 1 all the way up to the front, and we're left with negative 1 times the minus state, right? Or negative 1 to the 1th power, because that's also equal to negative 1, right? And then, since this is the y equals 1 case, we can also write this as negative 1 to the y power times the minus state. Thus, we have just proven that this expression is true, right? 1 over square root 2 times y XOR 0 minus y XOR 1 equals negative 1 to the y power times the minus state, where y is either going to be 0 or 1. So from this, we know the conclusion we can draw is that XORing the minus state with some arbitrary bit y is equivalent to multiplying the minus state by the phase negative 1 to the y, right? This is powerful information because this means we can now apply a phase of negative 1 to the y power to any state we want as long as we tensor it with y XOR minus state, right? In other words, since y XOR minus state is equal to 1 over square root 2, well, well, yeah, this expression right here. Yeah, 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 that's fair. Does this make sense? Okay, okay. I want to make sure like this isn't confusing and you're able to understand this perfectly. Okay. Yeah. Anyways, since we know this to be true, we can have that x, some arbitrary state, whatever, it can be whatever state you want, tensored 1 over square root 2 y XOR 0 minus y XOR 1 is equal to the arbitrary state x tensor negative 1 to the y power times the minus state. And this is just like a remark. One way you could do this would be using the C0 gate, right? C0 operation with the control bit being B1 and the target bit being B2 is equal to the B1 state tensored B1 XOR B2, right? That's an identity we proved last time. And then, if you plug in y, the either 0 or 1 for B1, like the control bit, and the minus state for the target bit, like B2, then you're able to get this. Y tensor, y XOR minus state. That'd be like one way you could actually do this in practice. Anyways, since we can apply a phase of negative 1 to the y power to any arbitrary state x, would it be a good idea to have x represent the inputs of the Deutsch-Jozsa problem, right? It'd be like a bit string, right? Some of length n, and you just plug it in, right? We're gonna have x represent that input, the thing you want to put in, and have y be some value dependent on x. In other words, have y be a bit like that is a function of x, right? Why would this be a good idea? Doing this gives us the ability to mark an input with a phase that is dependent on the input value, meaning the phase now carries information about the input and can be used as a tool to manipulate the state at a later time. What I mean by the phase carrying information about the input is that if we're able to know the value of the phase, doing so will allow us to glean properties that the input possesses. For instance, let's say we have some arbitrary input x1 for x1, if we find the value of its phase to be -1, we know that x1 is a value such that when it's plugged into yx, right, the function yx, right, it will return 1. And if we find the value of the phase to be +1, yx1 will return 0. Since the phase is equal to -1 times y of x, if -1 to the y of x equals 0, then obviously like y of x must equal 0. Now, regarding my statement that the phase can also be used as a tool to manipulate the state at a later time, I'm sorry, but I can't really find a way to make this clear right now, but I promise it will illuminate itself later on. But for now, the only intuition I can sort of provide is that a property of phases is that phases of opposite signs cancel out while phases of the same sign add together. This suggests that since the state now has a phase attached to it, some step down the line will cause parts of it to cancel out or add together. Oh yeah, and if it isn't obvious, the function of x we should set y equal to is f of x, the mystery function that we are trying to categorize as balanced or constant, right? Just to make sure, are you able to understand? Okay. Let's recap what we have so far. For an arbitrary input x and y equals the mystery function f of x, right? We have x tensor, the 1 over square root 2, y XOR 0 minus y XOR 1 equals x tensor, 1 over square root 2, f of x XOR 0, right? F of x being y, or also the mystery function, minus f of x XOR 1, right? And that is going to be equal to x, right, tensor, -1 to the f of x power, substituting f of x for y, times 1 over times the minus state. So what we have constructed here now is a way to apply a phase dependent on the output of f of x to the state at x, right? In other words, for any input x of f of x, we're able to mark all inputs for which f of x is equal to 1 by giving it a phase of -1, and mark all inputs for which f of x is equal to 0 by giving a phase of +1, which is the identity, which is the same thing as doing nothing to it. Anyways, let's say that somehow we're able to gather all 2 to the n phases assigned to all 2 to the n inputs, given that our input is a bit string of length n, right? For any f of x that takes in a bit string of length n. So sorry, to recap, if we have a bit string of length n, then we have a total of 2 to the n different possible inputs, right? That we have, right? Let's say we are plug in every single n digit inputs, right? And then we collect all the 2 to the n phases for all those 2 to the n inputs, okay? That's what I mean to clarify. Anyways, in the case that f of x is balanced, you would have 2 to the n minus 1 phases that of +1 and 2 to the n minus 1 phases of -1. In other words, half the phases would be +1 and half the phases would be -1, right? In the case that f of x is constant, you either have 2 to the n phases that are all +1 or 2 to the n phases that are all -1. The reason why in this case is because every single input, right, n-bit input would either give you 0, they would all give you 0. In that case, would be the phase of +1, right? And if every single n-bit input gives you 1, you'd have 2 to the n phases of -1, yeah, because it's constant. They'd all have the same output. Anyways, given these two scenarios, what would be a procedure you could do to the phases without knowing exactly which case it falls underneath, what the phases are exactly, that would help you distinguish between these two cases? One strategy that comes to mind would be to just simply add all the phases together and inspect the resulting sum. Let me show you why. In the case that f of x is balanced, since you have 2 to the n minus 1 phases of +1 and 2 to the n minus 1 phases of -1, each phase of +1 would be canceled out by a -1, because if you add those together, you get 0, and there's an equal number of both. In the case that f of x is constant, since you either have 2 to the n phases of +1 or 2 to the n phases of -1, your sum would either be 2 to the n or -1 times 2 to the n. This makes it really, really easy to distinguish between the two cases, constant or balanced, as adding all the phases together deterministically results in a 0 for balanced or non-zero for constant sum. One small disclaimer I have to make is that the actual Deutsch-Jozsa algorithm doesn't actually gather up and add all the phases like we just did, but it does something really similar, that it also has the end result of canceling out phases deterministically based on whether f of x was a constant or balanced function. Thus, we now have a general plan of action to solve this problem. Okay, just to recap, our goal is to measure qubits at the end of our circuit and output 0 if f of x is constant, or output some state x that is not equal to 0 if f of x is balanced. And then this is our step-by-step plan of how we're going to do this. What the circuit will look like is, first, we're going to prepare a superposition of all possible inputs. Second, we're going to apply some gate to the qubits that will assign a phase to each state in the superposition that is dependent on the value of the input it corresponds to. In other words, it applies a phase of alpha to the input state x, where alpha equals a value, some value dependent on the input x. Third, we're going to conduct some process that, 1, makes the phases of the 0 state increase so that the magnitude of the phase is equals 100%, and cancel out all other phases if f of x is constant, right? The reason why you want to do this is that, in the case that is constant, we want to deterministically always output 0, right? And the only way for us to do that would be to make the amplitude of the 0 state have magnitude of 1, right? So it'd be like 1 or -1, so that you'd have 100% chance of outputting that when you measure it. And if you have 100% chance of measuring the 0 state, then you have a 0% chance of measuring all the other states, right? And 2, make the phase of the 0 state cancel out and go to 0 if f of x is balanced, right? If the probability that you're going to measure the 0 state becomes 0, then you're basically guaranteed to measure any other state, right? Which is exactly what we want if the f of x turns out to be balanced. The last part of this process would be just to measure the qubits and output the result. And let's actually see what this looks like in practice in our Jupyter notebook.